All right, so in this video, we're going to be looking at methods for solving equations that involve trig functions. So we're going to start with the linear cases. We're going to work our way up to quadratic cases. And then we're also going to deal with some examples where the theta expression in our trig functions is not the same. We're also going to deal with equations that involve different trig functions. So let us get started. So our first example is just a simple linear trigonometric equation in theta, and there's only one trig function in the equation. So an example like this would be 2 sine theta plus 3 is equal to 2. So our idea would be first to isolate the trig function. So imagine what you would do if you just replace sine theta with x. What would be the steps that you would follow? So here I'm going to try to isolate the x term, which means isolating my sine term. So I'm going to subtract 3 from both sides of my equation. And so I would have 2 sine theta is -1. And then I would get the coefficient in front of my variable out of the way. So just as I would with 2x equals -1, when I have 2 sine theta is equal to -1, I'm going to divide both sides by 2. That's going to get me x isolated, or in this case, sine theta isolated, equal to -1. Now, at this point, I have to find the values of theta. So the question that I'm asking myself, what values of theta, when I put it into the sine function, are going to get me -1/2? Now, typically, I'm going to need to find all the values between 0 and 2 pi, although sometimes you will see problems where they find them between -pi and pi. But in a lot of textbooks, they're asking for 0 to 2 pi. So in this case, we think about our unit circle. If we use our inverse trig functions, we will not get all of the values. Typically, there was 2 values for most of these answers, and that'll only give us one of them. And so that's a start, but then we have to think about what other quadrant we can use this as a reference angle. What other quadrant would that angle be in? So if we use the inverse trig function here, we're going to get an angle of -pi/6. This is in the 4th quadrant, so this isn't in the range of 0 to 2 pi. So we can add 2 pi to get to that value, but that's not the only one. We also get a sign that's negative in the 3rd quadrant. So what is the 3rd quadrant angle that has pi/6 as a reference angle? That's going to be 7 pi/6. So in this case, our solution set in the range of -pi/2 of 0 to 2 pi is going to be these 2 values, 7 pi/6 and 11 pi/6. Now, I have another video on doing tricks with your calculator to try to get your exact values out of your calculator. So for instance, if you do inverse sine of -1/2, you get this decimal. If it's a standard angle, then you can multiply this by pi and get it into a fraction form, and then use the convert to fraction button in order to convert that into the rest of the fraction that goes with the multiple of pi. Now, if this doesn't convert to a fraction, it's because it's not a standard angle. But for standard angle problems, you can do this. Now, for linear trig functions, if I have a multiple of theta, but only one trig function, then the procedure is going to be very similar, at least until I get the trig function isolated. So let's say I treat the 2 theta like just an alpha, it's a single angle. So then I'm going to try to get values in this case. Once my trig function is by itself, I'm going to say, okay, so what values of alpha are going to give me tangent of that angle is -1. So that would be -pi/4 initially. but again, that's not in this range. So I add pi to get into the second quadrant, and then I can add pi again to get back into the fourth quadrant in my standard range. So that would give me 3 pi over 4 and 7 pi over 4. And if this was just tangent of theta, then I'd be done. But it's tangent of 2 theta. So that's going to give me 4 solutions. And so I'm going to need to add 2 pi to both of these values in addition to the original ones. So 3 pi over 4, 7 pi over 4. And if I add 2 pi again, I'm getting 11 pi over 4 and 15 pi over 4. And then those are my alpha values. And then I take 2 theta equal to all of these, and I divide everything by 2. And that's going to give me 3 pi over 8, 7 pi over 8, 11 pi over 8, and 15 pi over 8. And if you check, even though I added an extra round of 2 pi, when I did my divide by 2 here, I ended up with all of these values being in between 0 and 2 pi again. So this is something that I'm going to have to do anytime I have a multiplier of theta. If I had a 3 theta instead, I would need to multiply the set of values until it was 3 times as big. So I would get, instead of 2 solutions, I would get as many as 6 solutions. And so I would have to have another set of adding 2 pi to these values. And then when I divided by 3, I would get 6 solutions. And again, you'll be able to double check after you actually isolate theta that you'll have all of the resulting values in the range of 0 to 2 pi. Now, if I have a linear trig equation, it's in theta, but I've got stuff going on inside of the trig function. Again, I'm sort of mentally going to say, I'm not going to worry about all that stuff. I'm first going to deal with the trig function. And so I'm going to replace all this nonsense with alpha, and I'm going to figure out what values of alpha are going to get me cosine is equal to 1/2. Now, when I end up dividing theta by a number like this, I actually get fewer solutions rather than more. So I may end up with 1 solution, I may end up with no solutions, but I still should start out with at least enough solutions to get me into that 0 to 2 pi range, and then I can go from there. Now, first of all, the inverse cosine of 1/2 is going to give me pi over 3. I'm also going to get another one in the fourth quadrant, negative pi over 3, where cosine is also positive. Now, once I do that, then I replace, once I have my list of possible theta values, then I replace alpha equal to those solutions with this crazy expression in terms of theta, and then I do algebra on each of those solutions. So I'm looking at pi over 3. If I do my calculations here, I'm going to get here pi over 3 minus pi over 4, or theta over 3 minus pi over 4 is pi over 3. I'm going to add the constant to both sides and get this. And then I'm going to multiply both sides by 3 and get 7 pi over 4. This is in the range of 0 to 2 pi, so I'm good. Here, I'm going to do the same thing. I set my expression inside my trig function equal to my other solution. I add my pi over 4. I multiply by 3. This is not inside the range of possible solutions, so I don't need it. If I do this with any other examples, I'm going to find that they actually fall outside the range of 0 to 2 pi, and so I don't actually need those values. I have just the one solution, 7 pi over 4. Now, quadratic quadratic equations. In this case, I don't have a linear term. I just have the regular squared term and the constant. So I can solve these by essentially isolating my trig function and then taking the square root. And so that's what I'm going to do here. Again, pretend the trig function is like x. So what would you do to solve this equation? Well, I can move the 3 over to the other side, and then I divide out the 4, and then I take the square root, and I end up with my cosine theta. Again, essentially my variable is plus or minus the square root of 3 over 2. This is a standard angle. If I find the inverse trig function of both of these, I get pi over 6 and negative pi over 6 and 5 pi over 6 and 7 pi over 6. And adding 2 pi to the solutions, I get 11 pi over 6 and so forth. Those are my reference angles. And notice I'm getting 4 solutions because when I take a trig function with 2 solutions and I square it, I end up doubling the possibility for the number of solutions because I have a negative version and a positive version. Now, if I have a linear term, then again, I'm going to imagine that I'm replacing, like a substitution, my trig functions with just like an x. And that's going to give me a quadratic equation. So I'm going to end up with an equation. Mentally, I'm thinking 2x squared plus x minus 1. I can factor that, or I can use the quadratic formula if necessary in order to get my possible solutions for x. So here I get x equals 1/2 and x equals minus 1, which means that my cosine values are 1/2, or cosine is negative 1. Now, the 1/2 solutions are going to give me the possibility of pi over 3 and 5 pi over 3. But there's only one solution for this in the 0 to 2 pi range, which is pi. So 1 and negative 1 are the only times that I'm not going to get 2 solutions. All of the other values that I could get for this cosine function are going to give me 2 values, but 1 and negative 1 are only going to give me 1. So in this case, I end up with 3 solutions. Now, if I end up with any values that are outside the range of negative 1 to 1, then there is no cosine value, no angle value that will get me that value for cosine or sine, because those values are restricted to negative 1 to 1. So then I would just throw it away because there would be no solution. Now, if I have different trig functions in the same problem, then if they're related via a Pythagorean identity, then I need to make a substitution in order to get them to all be the same trig function. So here I have secant squared and tangent, and I know that there's an identity, secant squared is equal to 1 plus tangent squared. So I'm going to do that replacement for secant squared. That will turn my equation into this. And then I can proceed similarly to the previous problem using the quadratic formula in this case to try to obtain a solution. Now, what happens in this particular problem is that I get a complex solution. And that means that this is never equal to 0. You can see from the graph, it never crosses the x-axis. And so we have no angles. We just say there is no solution because we don't have angles that can produce complex solutions for tangent. For trig functions where they're only linear, but they have a matching theta, but mixed trig functions. So if the coefficients are the same, then what we can actually do is we can square both sides of the equation. Now, the reason that there is an advantage here to doing that is that when you FOIL this out, you get a sine squared and a cosine squared, which you can reduce to 1. And there is a double angle formula for this middle term here. 2 sine theta times cosine theta turns out to be sine 2 theta. And so when I substitute that into my equation, I actually now have a problem that is similar to one of our previous examples. I can find values that are going to satisfy this. from 0 to 4 pi initially, because it's times 2, and then divide those by 2. Now, because this is 1, I'm not going to get 4 solutions. I'm only going to get 2 solutions because there's one solution one time around the circle, and then a second solution the second time around the circle. And so when I divide those by this 2, I'm going to get these answers. Now, because I squared it, I'm actually finding solutions for both sine plus cosine is equal to square root of 2, and also sine plus cosine is negative square root of 2. So I have to find out which is going to be the correct value. They might both work, or only one of them might work. So I have to check both of these in the original equation. And it turns out that 5 pi over 4 gives me the negative square root of 2, and regular pi over 4 gives me the positive square root of 2. So that turns out to be the only solution to this problem. Now, there are some other sort of random weird ones that get thrown into the problem. And so these can be a little bit trickier. You have to be sometimes a little bit more clever. It's impossible to list all the conceivable scenarios, but typically these problems will reduce to ones that we've already done. So if you see something like this, cosine of 2 theta has 3 different identities that involve theta. One of them is cosine squared minus sine squared. That would get you just a sine squared and cosine squared term in your problem. That might be an option. Cosine 2 theta also has an identity that involves only sine squared. So it's 1 minus 2 sine squared theta. I recommend using that one because then you don't have that cosine squared to worry about. And everything is just in terms of sine squared and a constant. And then that will reduce it to that first quadratic example that we saw. If you choose the wrong trig identity, you can just choose another trig identity to further reduce the problem. But the best one to choose for this example would be to try to choose the cosine 2 theta identity that matches the term that's already in the expression. So if you had a cosine squared, you would choose the 2 cosine squared minus 1 identity. Here you have a sine squared, so you choose the 1 minus 2 sine squared identity. Now, if we have something like this, then what I would recommend doing is applying your double angle identity and rewriting sine 2 theta as 2 sine theta cosine theta. And then that combines the sines into this expression. Move your cosine over to the other side of the equation, factor out your cosine, and then you can go from there. Cosine theta is 1 factor. You pull that out, you solve for where cosine theta is 0. And then this one you can solve by the same way that we did in a previous example with just a quadratic solution. If you have a bunch of expressions like this where the angles are not the same, we want to try to make the angles all similar. So for instance, if this one is a 2 theta and this one is a 4 theta, we might want to apply the double angle formula in order to get them all in terms of 2 theta. In terms of 6 theta, we might be able to use a sum and difference formula to separate this into 2 theta and 4 theta. We could try to get them all the way down to theta, but that's probably overkill. We just need the angles to be the same. And so you want to try to do the least amount of algebra necessary in order to get them down to similar angles. But if you had a sum and difference formula for 6 theta, where you could reduce it to statements involving 2 theta and 4 theta, you could then reduce everything to 2 thetas, the whole expression, and not have to worry about like the half angle formulas where you get 3 theta, and then what do you do? So again, try to think about it in terms of how can I make these similar? Now, if you have an expression like this, where you have with 3 or more trig functions, or the trig functions are not related in any way by a Pythagorean identity or other kinds of common identities, then the best thing to do here is to reduce everything to sine and cosine and eliminate the denominators, and then this will reduce the problem typically to a previous case. Now, if you have combinations of trigonometric functions with algebraic expressions or other kinds of properties, the only way to solve these, generally speaking, is graphically. You have to put them into your calculator and solve them by numerical approximation, which is what the calculator does, because you can't solve these algebraically. You have x's in weird places. There's no way to get sine x equal to x and have a nice value. So you can only do them numerically. You can restrict your window to the range of 0 to 2 pi. Again, you don't need values outside of that typically. The number of solutions might be infinite, or it might actually just be a particular value depending on exactly what else is going on in the problem. So use the intersect function on your calculator to get the answers. Don't try to use trace because it's going to jump too much and you're not going to get a good result. You're going to want to use a more accurate method, which involves using the intersect function. But these really can't be done by hand. They have to be done with technology.